right, good morning. Just notice this thing. All right, so good morning. We look at the syllabus where it felt at first like we were going kind of slowly, and then suddenly we're going through a few sections that I thought we'd need more time for, going faster. So going to adjust, going to adapt. Today we're going to talk about kind of the generic mass balance approach briefly to setting up some equations. We'll talk a little bit about how that's going to impact equilibrium equation reactions, but mostly we're just kind of keeping the context similar to the electroneutrality equation, building a system of equations that we could use to solve for an unknown. Along with that, we're going to look at proton balance equations, which are a little special and are pretty similar feeling to the concept of acid neutralization capacity, which we'll get to later in the semester. Okay, so I also realized as we were a couple minutes late to getting going that I forgot to print something I need to print for my next class. So I'm going to try to end us at least 5 or 10 minutes early today, but I think we'll get through that. We're going to do just like we did last time and go through several cases, and we're going to do it for both the mass balance and the proton balance. And at the end, we'll look at a table that shows essentially all those cases put together, so we can kind of get a feel for a given example or for a given situation like pure water, what are we doing? How do we set up that equation of one sort or the other, and how can we pair them to use them together? So that's kind of the goal today. And of course, mass balance equations are pretty commonplace. This part's not going to be a big surprise. This is almost the same as saying we have stoichiometric relationships, right? So we've seen this kind of stuff quite a bit. And in general, we want to begin by writing up a generic equation and then solve from there as needed. And again, the context is if we can combine multiple equations, that gives us tools to solve for multiple unknowns. Okay, so pure water. When we say let's make a mass balance on pure water, what are we talking about? Well, really, we're going to set up a mass balance on the constituents there, in particular the ionic species. So we could say H2O is going to be dissociating into H plus and OH minus. There's a one-to-one relationship there, so we can say essentially that H plus equals OH minus, at least when we're neutral, right? As to the extent that water dissociates, and if we have pure water and nothing else, then it should be neutral. That's what it's going to look like. Okay, so pretty similar. That's also the electroneutrality equation, the cations equaling the anions. And as we'll see, this is also the same equation for the proton balance. Kind of makes sense. It's the very simplest case of what we can do with aqueous chemistry, right? Okay, so that's the mass balance for the pure water case. Now, once we get to something like an acid where we have HA, H being the proton and A being some acid that's can release that proton, we can say that this will give us H. Some of it will stay in HA, some of it will be H plus, some of it will be A minus. Those are the forms that we'll get in the system. And what we want here is a mass balance on essentially how much HA is there. So we can write it and say, well, the HA plus this A minus is equal to the total amount of this acid in any form. So there's a key concept here that we're going to use quite a bit, and that is that for a given acid, and hypochlorous acid is a common example that I use for disinfection type stuff, right? So H and then our OCl in the case of hypochlorous acid is our A, is going to be in equilibrium with H plus, and then A minus, in this case OCl minus, right? That's the A minus. So when we do some sort of acid like that, some sort of chemistry, what we're saying is that the amount of OCl in this solution is not changing. We have, if we had 1 mole of HOCl, then we have 1 mole total of OCl in one form or the other. So it's just that terminology, we're going to say we have some total. So we can use that subscript T there. Later on, we're also going to go in a little bit more depth, because we can also say we have some fraction alpha of total. Maybe we could say fraction of OCl minus would be the OCl minus divided by the total, which we could describe as OCl minus plus HOCl. Several ways to write that. You've probably seen this before, and one of the assignments we will get to is working on calculating, okay, what's the fraction at a particular pH. And in fact, I think there's some bits and pieces of that in the homework that I've posted. So I did post your homework Friday if you didn't see that, and a MATLAB assignment as well. Okay. So that's the situation there. Speaking of MATLAB, did we have something due today, or is that Thursday? Thursday. Okay. And have you guys started that yet? Not yet. Okay. Just curious how it's going if you have. So I'll ask again on Thursday. Okay. So we're gonna come back to these concepts and use them more often. I think you've seen them before, and if not, we'll make sure you're comfortable with them. But it's again a part of that setting up a mass balance to understand what's in the system, and then describing that in terms of fractions of total. In this case, a lot of times we would combine an equilibrium reaction with this mass balance type of formulation. So we could substitute some sort of equilibrium reaction into here, or equilibrium constant, knowing something about H plus, to find out what this ratio is given some pH, for example. Okay, so coming back to the case number 2, we can say that the total is HA plus A minus. Pretty straightforward. Case 3, if we have this situation where we have this Na, so sodium plus that A, to release A minus, what would have been an acid, I guess it's the conjugate base, right? So it would have released a proton, but instead we've added it as sodium. In our example, we could say sodium hypochlorite, right? So instead of HOCl, we could add NaOCl. It's pretty commonly done with bleach, right? Okay, so if we add something like that, then what we can say is the total amount of A is also equal to the total amount of sodium, because for every 1 A we added 1 sodium. So that's at least 1 mass balance relationship we can set up there. Does that make sense? So it's kind of just looking at the stoichiometry and saying, oh, we can make a relationship that we know this is going to hold true, assuming this is all that's in solution, right? There's no other sources of sodium or A. So the total amount. Now, we will note that there will, certainly will be some A minus and HA in here. That will also hold true, but we can just describe it as A total. Okay, in case number 4, we've got pure water plus H2B. So it's kind of adding something like H2CO3. So this is kind of adding an acid sort of thing. We can use the same exact type of circumstance, or same exact type of analogy, to say that the total amount of B in whatever form it's in is going to be the total amount of B, right? we can assume that we have some H2B, some HB minus, and some B2 minus in this particular type of situation. So again, an example could be H2CO3 and HCO3 minus and CO3 2 minus. And in this case, that would be essentially the total carbonate. So it's pretty self-explanatory. We just want to make sure that we are tracking each piece because we assume there will be at least some of each piece in solution. Now, once we go to apply this in a little more practical manner, or in a little more practical scenarios, we might say that, oh, at a very basic pH, we have practically zero of this carbonic acid because it just won't exist to much of any extent at a basic condition, or something like that. So maybe once we're applying this, we might look at the conditions and say, okay, well, this one's approximately zero, so we'll simplify our equations and calculate accordingly. But as we develop them, we should probably go ahead and write everything out and recognize that by mass, B total is comprised of each of these. Okay, next common case would be where we have NaHB. This would be like, very similar to our last one, so we could say sodium HCO3, something like that. And here, in addition to the equation we just had a moment ago, we can also say that the total B is going to be equal to the total sodium we added, right? Because for every mole of NaHB we add, we get 1 mole of sodium and we get 1 mole of B, even if B disproportionates or fractionates or whatever. So we could also say then, in this scenario, sodium would also be equal to exactly what we were just writing, H2B plus HB minus plus B2 minus. Right, and so now you can start to see how we may have some useful tools to say, oh, okay, well, given some known parameters, we can solve this equation, right? And you can imagine we could substitute something else instead of sodium. This is just a common case example for us to look at, but if we did something like calcium, CaB, because Ca has 2 charge, it would be fairly similar, right? So we could have, for every 1 calcium, we'd have 1 B in that circumstance, and we could look at all sorts of different ways, and maybe we have Na2B, which is probably the next one, yeah. So, okay. So case 6 then, Na2B. This time we're not, we have a difference that for every 1 B, we have 2 sodiums. So the sodium concentration would be equal to twice the B concentration, if I said that correctly. So for every Na2B molecule we dissolve, we get 2 sodiums and 1 B. So the mass balance, again, it's quite obvious, I hope. It's almost boringly so. But just elaborating this to make sure that we see what's going on in each case. It gets a little more interesting for the electron neutrality and for the proton balance, I think. Okay, good on those 6? Making sense? All right. So let's do a couple quick examples just to get the going through the motions here. So we have a task to say, write the general mass balance equations for a solution of some initially pure water plus some NaCl. And I went ahead and let us kind of read part of the solution here. So before I do that, just take a moment to think about, okay, what are these mass balances? What do we need? And then we'll read through this and then see if you got the equation. All right, so we could probably write H plus is equal to OH minus. Don't think that's really what the book is going for. But the only other thing in solution is the NaCl, so we could at least write the amount of sodium is equal to the amount of Cl minus the chloride, right? Which I think is, yeah, exactly what they're going for. So pretty straightforward, and the book's explanation is just, well, the salt is not doing anything to H plus or OH minus that would affect that, so we could use that H plus equals OH minus. But the only other thing that might be relevant is the relation between Cl minus and Na plus. Of course, we could also do a electroneutrality equation here and add up the positives and the negatives and all that, but this is mass balance. Okay, another one. Let's take something a little more complex and say we have 10 to the minus third formula weight of NaCl and 3 times 10 to the minus fourth formula weight of acetic acid, which can be represented as HA. They're placed in 2 liters of initially pure water. For this solution, write the general mass balances and the corresponding specific ones. So I don't think we need the periodic table here because we're given formula weights, and we should be able to, that means that that number of moles of this stuff before it dissociated, right? So 10 to the minus 3 moles of NaCl per liter, and we're doing this in 2 liters. So let's go ahead and take a look at what the book says. Now, for the mass balances, we can kind of know on a simple level, sodium is equal to chloride, and then with the HA, we can recognize that there's no other contribution to protons, so the H plus is going to be related to the A minus. I don't think we can add any other features there, and then it would be a matter of applying more specifics if we were trying to solve something in particular. Okay, so the Na is equal to Cl minus, and we can calculate each of those just to say that 10 to the minus third divided by 2 liters, that gives us moles per liter. That's chloride, which is also equal to the sodium, which is 1.5 times 10 to the minus third moles per liter. For the total acetic acid, we have HA plus A minus is equal to the total. And so we can have a total value that we added here, but we can't really discern exactly how much is A minus versus H plus without knowing anything more. In this case, also 1.5 times 10 to the minus fourth moles per liter. All right, does that make sense? Okay, and these are all quite simple, probably too simple to keep our interest, but the deal is we can use these in combination with the other equations in order to solve a larger problem. Okay, one more. We've got 3 times 10 to the minus third formula weight of sodium bicarbonate, or sodium carbonate rather, which can be represented by as Na2B. This is placed in 2 liters of initially pure water. For this solution, what are the general mass balances and specific ones? So we know that for every sodium we have 2 carbonates, so 2 B totals. And we can also write B total as H2B plus HB minus plus 2B2 minus. Now, one thing we'll notice here is, let's see, is that 2, should that 2 be there? I don't think it should be there. I think they made a mistake. Let me see if you agree. So B total, this should be the sum of each component, right? So this should be the CO3 2 minus plus HCO3 minus and the H2CO3. I think they were getting ahead of themselves because that would be relevant in a different portion for the 2B2 minus. Yeah, because there's no reason that should be multiplied by 2 there. So I disagree with the book. Does that make sense? Okay. Yeah. Okay. And of course we have to do that in 2 liters, so that plays out accordingly. Okay, so I think that's all I want to say for the mass balances. Okay, so then we'll move on to proton balances, and these are, like I said, a little more interesting, a little trickier, so we're going to take a little more time to understand it. But the proton balance, we can't actually make a proton balance for every solution. We can only do so when we have a condition where we are at a particular point on the pH scale where we found an equivalence point with maybe some equilibrium reaction. So if we have an acid base at that pKa, I think that's where we are able to do a proper proton balance. And what it does is it accounts for the amount, the total amount of sources of H plus on one side of the equation and sources of OH minus on the other. And at a very simple condition, if we just take water, we'll see that it just looks like, well, H plus is kind of a source of OH minus because of our dissociation of water. So one source, one is the source of the other, and the other is the source of the first. And so that's just a very simple equation. But ultimately what we're doing is we're trying to add up the total amounts of each. We can note that under certain circumstances, this might be the same as an electroneutrality equation or a mass balance equation, but overall, it's more of a source of acidity and basicity. The term proton balance is kind of how chemists have referred to it, but it's not just protons. It's actually protons and hydroxide. So it's a balance of both. The book just says, well, we're going to keep going with PBE because that's convention. But it's an accounting for both, and it'll be the sources of OH minus on the left and the sources of H plus on the right. Okay. Water is a little bit of an exception, but in general, we can only write them when we find this special compositional point or points, an equivalence point. So when we look at some graph where we have pH versus some speciation diagram, these equivalence points where two species meet, those are the moments where we can do the PPEs as I understand it. Sometimes these are going to be independent of the mass balances and electroneutrality equations. Sometimes they'll end up being the same or reliant. We can build them from others. Okay, so we're going to take a look at the cases, and I'm going to do this a little more slowly, and we can learn from what it is to build one of these proton balances as we go. And we also have a table that gives us some instructions on like how do we build these, how do we set them up, and what do we check for. If we are able to set one of these up, that is an additional balance governing equation that we can use to say, okay, the total amount of acids and bases or sources of those meet at one of these equivalence points so that we can get a balance there. And develop that equation, use that equation in conjunction with others. So we're going to assume for each of these cases we look at, the 1 through 6 again, the same cases, we're going to assume that we have found that equivalence point for these. I think this is very related to understanding how titration works, and that so we'll get there later on as well. And I think the added context we get to later will make this more and more relevant and understandable. Okay, so the case of pure water, it's pretty obvious. You know, water dissociates. That's equation 4.1 apparently. So H2O dissociates into H plus and OH minus. Not a whole lot, but we'll get some of each. And then at that point, we know that in some sense, the formation of H plus is the cause of the formation of OH minus, and vice versa. So if we're writing on the right side of the equation sources of H plus, and on the left side of the equation we're writing sources of OH minus, then we get H plus equals OH minus for the case of water. Okay, does that make sense? Good enough for now? Okay. So, in general, what the approach we're going to do, which I kind of summarized a little bit, but wanted to just show the simple case first. To write one of these equations, we first have to verify that it's either just pure water, or we have a scenario where the acid or basic species, we are in one of the characteristic equivalent points. That makes this relationship valid. Then we're going to start with H plus equals OH minus because we're in an aqueous condition. We're doing aquatic chemistry, right, or aqueous chemistry. So that's going to be true, and we can just start there. And they'll be on opposite sides, and the first source of H plus OH minus. Okay, then on the OH minus side, we're going to add every concentration, every species, that when you form that species, so the genesis of that species leads to an H plus being released. So when I say the genesis of that, what we're talking about is when HA goes to form, H plus and A minus, well, to form A minus, we added an H plus. That's what we're referring to. So this is talking about this scenario where A minus led to the formation of an H plus. Okay, on the H plus side, we're going to do the inverse. Anytime we had something that led to an OH minus, we're going to have that there. Hope the crane doesn't drop anything on us here. All right. We might also need a multiplying factor if, for example, we had, let's say, H2, I don't know, I'll use C. H plus, we'll have a better example in a minute, plus C2 minus, something like that. We're getting 2 protons for every one, right? But in reality, what we're going to do is we're going to do it stepwise, right? One at a time. So we'll come back and talk about that. Going to hold off on the confusion, but we might have some multiplying factor because we're getting more than 1 proton per thing. Okay. So we can do that for the OH minus and for the H plus on the appropriate sides. And last thing we need to do is go through and check to make sure that we didn't put anything in our equation that was directly added. And what I mean by that is for this scenario here with HA. We do not include HA because HA was not formed to produce H plus or OH minus. It was the A minus that was formed, and in doing so we released the H plus. So if we add sodium hypochlorite, right, this would be like NaA. Then we're not going to add we're not going to add in the sodium part of that, if I'm saying that right. Oh, excuse me. We're not going to add in the A minus part of that, because when we form A minus, that did not release any H plus. It released an Na plus. So in that condition, we're not adding sodium to that condition. Excuse me, A minus to that condition, to that equation. Okay. All right. So we always place H plus on the left. It's a source of OH minus. We always place OH minus on the right as a source of H plus. That's by convention. It's just how we're going to do it. It also matches whenever we write like an electroneutrality equation and stuff. Okay. Any questions on this? It's probably not entirely clear. I probably didn't speak that last part very clearly either, but hopefully the point is coming across and the cases will elaborate for us. Okay, for the second case, pure water and HA. Here we have a source of H plus. So we would start with the water, right? So H plus and OH minus are going to be there. The only other thing we have here is HA and A minus. Now, only one of those species contributes to either adding H plus or OH minus. And we can see that when we form A minus, we get an H plus out, right? So that's why we're going to add the A minus on the right side of this equation. So does it contribute an H plus when it is formed? That's kind of the question. Okay, there's no other sources for OH minus, so there's nothing else on the left side of the equation. And that is basically that. Okay. One thing you'll notice again here is this is very similar to a charge balance equation where the got cations on the left and the anions on the right. That tends to happen, and what we'll notice, especially as we get into alkalinity and those equations, is we'll notice that some species, if they're added with an H plus or an OH minus, the cations are adding base and the anions are adding acid, unless you have a circumstance where you have like that sodium or something like that, right? Or a chloride instead of the OH minus. So you're going to start tuning into the fact that the cations and anions are either going to be added in a way where they don't contribute, or added in some way where they are contributing to the acidity and basicity, almost always. Sometimes we'll add something that is attached to something like carbonate, and carbonate is its own special thing because it's a little bit acidic. It engages with the acid-base chemistry, but it could also off-gas as, you know, and be removed from solution potentially, right? So all of these pieces are going to be around and relating to this type of system. Once we get there, whether or not the system is open to the atmosphere or not, or closed, also becomes relevant. Okay, so next up would be case 3, and this one's a little more, got a little more to think about here. We've got pure water and NaA. So what we can start with, before we develop the equation itself, we can take a look at, well, what happens when we dissolve NaA? NaA is going to give us the Na plus and A minus. And when we put the A minus in solution with water, that will be a source of OH minus. Because when A minus reacts with water, it can take a proton and release an OH minus. Okay, so we kind of have to think about, in that sense, when we add this, it's that conjugate base, that NaA, what it will do is react with water, and then water becomes, in a sense, a source of the OH minus. But the way we write the equations, it's not what is the source of the OH minus or the H plus, it's what, when formed, resulted in an extra OH minus or an H plus, right? So when we can write when HA is formed, an OH minus is released. Right? So that's how we have something that's contributing to the release of OH minus. Release of a base. Okay, so with that in mind, we can again start with our H plus on the left, OH minus on the right, and then we have one source that is impacting H plus or OH minus, that is this HA. So HA will be on the left, and we see here now we have a situation where we are no longer following a charge neutrality situation, because we're not accounting for A minus, and we have the H plus HA there, in the mix. So we're no longer following electroneutrality exactly. It will still hold true in the solution, but this particular equation is not precisely that anymore, like it was in the first one. And we're not directly dealing with the mass balance here either. So it's its own equation that will hold true for this case, right? So it is a separate equation. Okay, let's see. I think the text is hopefully saying all that stuff that I just said. Now, one thing that it's adding here is we notice in this scenario that the solution must be at least a little bit basic. And the reason for that is because our relationship here says H plus something is equal to OH minus. Now, we don't know exactly what concentration HA is, but because we expect that the equilibrium constant is not like infinitely large or small or something weird like that, there should be some amount of it. There should be at least a little bit of HA in solution, even if there's not a lot. And that's going to shift the balance here away from neutral pH, because there's nothing else that can affect the balance between the OH minus and the H plus. So even a little bit there, and we assume there is at least a little bit there, shifts this so that there's a little less H plus than there is OH minus. So that's why we say it must be at least somewhat basic. Okay, and with that in mind, some of these equations will tell us that. In fact, in the one before, if we take a look, we could say, well, this one must be at least a little bit acidic, right? And maybe it says it here. We'll write it. And of course, in the first case where we had just water, we kind of say, well, that's going to be neutral pH because nothing else exists in the water. pure water. Okay. Does that make sense? So sometimes we can learn something like that. As we'll see in a moment, sometimes we don't know for sure, but maybe with some extra information we could find it. Okay, so let's take pure water plus this H2B. This is sort of what I was alluding to earlier. So in this case, when we add H2B, we'll have to stop and think about, okay, what are all of our sources for acids and bases? Of course, H2CO3 is a good example for this. And in this case, we can even tell just by looking at H2B, it's going to be supplying protons because it has 2 of them for every B. And so the different forms we could find that might be relevant would be B2 minus, HB minus, and H2B, right? Now, in terms of which ones of these are going to form, are going to release a proton when formed, well, H2B, if we form it, that's consuming a proton. That's not going to do anything, right? So really, we have 2 that will form protons when they are formed. So we have B2 minus and HB minus, plus we have H plus and OH minus. So we start with, of course, these 2. And then from there, we go on and say, okay, well, when we form HB minus, 1 proton is released. Okay? So that we have HB minus there. Then when we form B2 minus, we are releasing essentially 2 protons. Now, this could get a little confusing, and I think this is where the book, I think, made that mistake earlier in writing it as 2 B2 minus. When we form B2 minus, you might think to yourself, well, we are forming it from HB minus, so it should just be 1. But the reference point is starting at H2B. And so from H2B, we're releasing 2 protons to get there. Because we're already accounting for how much HB minus was formed and stopped there. So the proper way to do that is to say, well, every B2 minus accounts for 2 protons. Therefore, there's that multiplication factor we needed, I mentioned earlier on when we talked about the table. So here's our multiplication factor. So when necessary, we add that stoichiometry, kind of. It's not stoichiometry really, but same sort of concept. Okay, there's no sources of OH minus in this condition, so we are left with H plus is equal to OH minus plus HB minus plus 2B2 minus. Yeah.
So considering case 2, why didn't we have like 2H plus then?
So case 2, 2H plus on the left.
Like you'd have H2 giving you like 1H plus and then OH minus, and then HA will also give you 1H plus and then A minus.
Okay, so you're saying that we have 2 sources of H plus, is what you're thinking. Remember, what we're doing here is we're not writing the sources of H plus exactly. We're not writing the sources of H plus on the left for sure. On the left, we're writing the sources of OH minus. And it's not even the sources, it's the molecules that, when formed, gave off an OH minus. So everything on the left side should be, when formed, released OH minus. And on the right side, when formed, released an H plus. So in that sense, only the H plus from water dissociation was releasing it. It's a good question. Okay. Another way to look at that exact dynamic is we can take a look at this table that the book has, and we can kind of look at the different conditions where we can form, and I'm sorry, I should have kept the caption here so it would probably make a little more sense. The conditions where we would have these different species. So considering water and B2 minus, we can recognize that for every water, there's a B, and B2 minus, we have 2 protons there. For every water and HB minus, we have 1 proton, right? We're kind of looking at how many protons are required to go there. Yeah. So it sort of charts that out as when things are being released for you. Okay, so the fifth case, we have pure water and NaHB. So this would be like sodium bicarbonate. And in this case, we get that first step is releasing the sodium and the HB minus. Now from there, the HB minus can go into back to H2CO3 or to CO3 2 minus, or rather H2B or B minus, or B2 minus, right? And we'll have HB minus. So given all of that, we can recognize that in this scenario where we started with NaHB, where's my cursor? Okay. Sometimes it's hard for me to find it. We have Na plus and we have HB minus. And so from that condition, from HB minus, we can form we can have this in equilibrium with H plus and B2 minus, or we can have HB minus in equilibrium with H2B and a proton. However, when we are going this way from HB minus, we can look at it as consuming a proton, or we can look at it as, in doing so, we are releasing NOH minus from water. Kind of how we looked at the second example, the second case. So let's see if the book can say that a little more clearly. So a portion will dissociate, giving 1 H plus and 1 B2 minus. Every B2 minus in the solution is then responsible for the presence of 1 H plus. So this is actually different than last time, right? Last time we had a 2 here. This time we don't, because we started at HB minus. So that starting point is kind of relevant here. From HB minus is where we started. Now we are releasing 1 proton there. So again, on the right, the things that added a proton to solution when we formed it. On the left, the things that added an OH minus when we formed it. So on the left, we've got H plus, on the right, we've got OH minus. We add that B2 minus here on the for the formation of 1 proton. And on the left, we're going to end up forming an OH minus. So, and it's describing this here, we have to have at least some H2B, can't be 0. And in doing so, that's going to be formed by this reaction like I showed, HB minus with H plus. For every H2B formed then, there is either one OH minus formed or one OH minus consumed. So maybe one way we could reasonably write this is put a minus H2B on the left side, and then we add it to both sides to get rid of the minus and put it on the other side. Right? So we can actually look at it that either way and it works just fine. So does that make sense? Okay, and under this condition, we actually don't know if this is acidic or basic, right? And that'll depend on the pKa of whatever point we're looking at within the NAHB system. Case 4, let's see, did we know? I think we're not sure. Well, this must be acidic, right? Because there's less OH minus than there is H plus. So at least a little bit acidic. Okay. Last case here, we have pure water and Na2B. So in this case, it's a little bit opposite of case 4, where we are releasing a bunch of protons. In this case, we're consuming a bunch of protons towards forming H2B, because we're going to probably have at least a little bit of H2B. All right. So as we, every time we form HB minus, we're consuming 1 proton. Every time we form H2B, we're consuming 2 protons. So really, it really is the inverse of the case 4. And maybe we could have started by saying, like we always ought to, is start this way. H plus is equal OH minus. And then we could say, well, we're consuming protons. So we could have a minus over here instead of releasing protons. We'd have a minus for every time HB minus is formed, we've consumed 1. And for every time we form H2B, we've consumed 2. And then we move those to the other side, and we end up with the equation here. Right? Okay. So what we ought to note here is it's whatever we start with, how many protons or OH minus are released or consumed to get there to the balance. Or to get to the other species. That's the question. Okay. So a summary table for the electroneutrality, the mass balance equations, and the proton balance here. We have all 6 cases shown here, this table 4.2 in our book, and we can take a look at all of them. What we'll find is, in the case of pure water, they're all the same. We end up with the same conclusion. We'll notice that in some cases, we've excluded some terms in the proton balance. That's the only one we're doing that, because, well, I guess in the electroneutrality, we're excluding the non-charged species, right? So the mass balance, we're adding whatever's relevant or what we can make a relationship for. The electroneutrality equation, that is doing all the charged species. And the proton balance is anything relevant to the formation of protons or OH minus. So we could take a look at all those. And then one thing we'll find, as the book notes, is sometimes we can find a proton balance given some combination of the mass balance and electroneutrality balance. So I think that's the examples here. So we've got several here. Let's take a couple minutes to consider these specific situations, and the task is to then write a mass balance for each of these solutions. For a moment, we're going to say, though, that HA is going to be acetic acid. NaA would be sodium acetate then. H2B is going to be carbonic acid. HB minus is then bicarbonate. B2 minus is carbonate. NaHB, sodium bicarbonate. Na2B is then sodium carbonate. Okay, so we want equations, PBE equations, sorry, proton balance equations, for the solution of acetic acid, for sodium acetate, for carbonic acid. And what we notice here is this is basically cases 2 through 6. So take a moment to just reflect on that and see if this is coming to you intuitively. It's sort of just a recap of what we just did. And you can go ahead and put it in the chemical terms instead. All right, I see some of you going back and checking, which is totally fine, but we might as well just show you here to let you double check yourself. My point here is just to see, like, are you thinking about, okay, what is releasing an H plus upon formation, right? What is releasing an OH minus when it's formed? that making sense? Good on that? All right. So I'm going to leave it off there. We'll pick up and kind of do just a little bit of review for the last example problem there next time. And perhaps we'll talk a little bit about MATLAB too. Okay. All right. We'll see you on Thursday.